Hello students, today's we shall study about hydrogen spectrum, Lyman Balmer Paschen series. So let's start. Hydrogen emission spectrum. We all know that electrons in an atom or a molecule absorb energy and get excited. They jump from a lower energy level to a higher energy level and they emit radiation when they come back to their original states. This phenomena accounts for the emission spectrum through hydrogen 2, better known as the hydrogen emission spectrum. In the late 1800s, it was known that when a gas is excited using an electric discharge and the light emitted is viewed through a diffraction grating, the spectrum observed consists not of continuous band of light but of individual lines with well-defined wavelengths. Experiments have shown that wavelengths of the lines were characteristic of the chemical element emitting the light. They were an atomic fingerprint which resulted from the internal structure of the atom. What is hydrogen spectrum? The hydrogen spectrum is an important piece of evidence to show the quantized electronic structure of an atom. The hydrogen atoms of the molecule dissociate as soon as an electric discharge is passed through a gaseous hydrogen molecule. It results in the emission of electromagnetic radiation initiated by the energetically excited hydrogen atoms. The hydrogen emission spectrum comprises radiation of discrete frequencies. These series of radiation are named after the scientist who discovered them. Hydrogen spectrum wavelength. When a hydrogen atom absorbs a photon, it causes the electron to experience a transition to a higher energy level. For example, from n equal to 1 to n equal to 2. When a photon is emitted through a hydrogen atom, the electron undergoes a transition from a higher energy level to a lower, for example, from n equal to 3 to n equal to 2. During this transition from a higher level to a lower level, there is a transition of the light occurs. The quantized energy levels of the atoms cause the spectrum to comprise wavelengths that reflect the differences in these energy levels. For example, the line of 656 nm corresponds to the transition from n equal to 3 to n equal to 2. This is a picture of various series, Lyman series, Balmer series and Paschen series. For Lyman series n1 equal to 1, for Balmer series n1 equal to 2 and Paschen series n1 equal to 3. In another picture you can see the Lyman series, Balmer series, Paschen series and bracket series. Hydrogen emission spectrum. In 1885, on the basis of experimental observations, Balmer proposed the formula for correlating the wave number of the spectral lines emitted and energy cells involved. This formula is given as 1 upon lambda equal to frequency equal to R, that is Rydberg constant, 1 upon n1 square minus 1 upon n2 square. This series of the hydrogen emission spectrum is known as the Balmer series. This is the only series of lines in the electromagnetic spectrum that lies in the visible region. The value 109677 cm inverse is called the Rydberg constant for hydrogen. The Balmer series is basically the part of the hydrogen emission spectrum responsible for the excitation of the electron from the second cell to any other cell. Similarly, other transitions also have their own series names. Some of them are listed below. Transition from the first cell to any other cell, Lyman series. Transition from the second cell to any other cell, Balmer series. Transition from the third cell to any other cell, Paschen series. Transition from the fourth cell to any other cell, bracket series. And transition from the fifth cell to any other cell, Paschen series. Formula is given here. Johannes Rydberg, a Swedish spectroscopist, derived a general formula for the calculation of wave number of hydrogen spectral line emission due to the transition of an electron from one orbit to another. The general formula for the hydrogen emission spectrum is given by 1 upon lambda equal to frequency equal to R, that is Rydberg constant, 1 upon n1 square minus 1 upon n2 square, where n1 equal to 1, 2, 3, 4, n2 equal to n1 plus 1, V equal to wave number of the electromagnetic radiation, and the value 109677 cm inverse is known as Rydberg constant for hydrogen. Again the formula is given here. You have to remember this formula for solving many numerical questions. 1 upon lambda equal to frequency equal to r 1 upon n1 square minus 1 upon n2 square, where v equal to wave number, lambda is equal to wavelength, r is Rydberg constant, n1 and n2 have integral values as follow. For Lyman series, n1 equal to 1, n2 equal to 2, 3, 4, etc. and their main spectral lines fall in ultraviolet region. Balmer series, n1 equal to 2, n2 equal to 3, 4, 5, main spectral lines fall in visible region. Paschen series, n1 equal to 3, n2 equal to 4, 5, 6, main spectral lines fall in infrared region. Bracket series, n1 equal to 4, n2 equal to 5, 6, 7, main spectral lines fall in infrared region. For fund series, n1 equal to 5, n2 equal to 6, 7, 8, and main spectral lines fall in infrared region. Rydberg constant, you may remember in this way, r equal to 109675 centimeter inverse. Again the series is shown here. First Lyman series, then Balmer series, then Paschen series, then bracket series. Lyman series formula. The formula for Lyman series is 1 upon lambda equal to r 1 upon 1 square minus 1 upon n square, where n equal to 2, 3, 4, etc. r is Rydberg constant. These transitions emit ultraviolet photons. Balmer series formula 1 upon lambda equal to r 1 upon 2 square minus 1 upon n square, where lambda is the wavelength, r is Rydberg constant, and can have any integral value. Paschen series formula 1 upon lambda equal to r 1 upon 3 square minus 1 upon n2 square, n2 may be 4, 5, 6, etc. For shortest wavelength, n2 equal to infinity, then 1 upon lambda equal to r 1 upon 3 square minus 1 upon infinity square. When we solve it, we will find 1 upon lambda equal to r upon 9 or lambda equal to 9 upon r. It comes to 820.4 nanometer. Which of the following, let us solve a question. Which of the following series of transitions in the spectrum of hydrogen atom falls in visible region? In visible, yes, visible region, find out visible region. The first series Lyman fall in ultraviolet region, second series Lyman, then second Balmer falls in visible region, then third, fourth, next series falls in infrared region. So the answer is Balmer, option C. Option C is the correct answer. The details are given here. Some more solved questions we shall see in the next video. So till then, continue studying. Have a nice day. Take care.